we're finally ready to go ahead and have our formal definition of a convergent sequence. I've held off on this for a while because the formal definition of convergence is very difficult to read. Part of the reason for that is that it took mathematicians probably hundreds of years to really hammer down exactly what was meant by convergence and to come up with this. And so you're unpacking a huge amount of history and revision when you read just this brief 3-line definition. So take a look at what it formally says, and then we're going to break it down bit by bit and relate it back to the things we've seen so far. So very formally, a sequence A sub n is going to converge to a number L, the L is the limit, if for every positive number epsilon, that's what this little E-like symbol is, it's the Greek letter epsilon, if there exists an integer big N such that, and let's read those absolute value signs as difference or distance, such that the distance between the term and the limit is less than epsilon, as long as the index on the term is greater than the big N. Again, that should sound like garbage to you because it's a lot of letters and it's a lot of history all packed down into a very small space. So let's have a picture and let's have a discussion of what the big idea with this definition really is. All right. The first set of symbols we see is the A sub n. Those are the terms of the sequence. We've discussed that previously. The L is standing for the limit, so I can keep that one straight in my head. If we're converging to a number. Let's call it L for limit. The next big scary symbol that comes up is this epsilon, a Greek E for that eh sound. And that eh sound is for error. So that's what the epsilon is meant to represent. It's meant to represent an error, and it's meant to be a small positive number, a tenth, a 100th, a 1000th, whatever it might be. It should be a really small positive number. The idea is that the terms of our sequence will never actually reach the limit value. We're getting really close. We're getting closer and closer and closer, but we're never there. And the error is trying to measure how far away we are from our ultimate end goal. The limit is the perfection. The term is where we actually are. Those two things are not the same, but if we're really approaching something, there should be a very small difference between those two numbers, a very small error. So that's what the epsilon is meant to do. It's meant to be a very small positive number. If you want, in your head, just picture a tenth or 100th, like 2 decimal places of accuracy kind of idea. Okay. I didn't say capital N, even though that's a more refined way to say this symbol. I said big N, because I want you in your head to think of this N like a really big number. 100 might do, 1,000 might do, 1,000,000 might do. It's standing for a big number. This capital N, the big N, has to do with the indices of your sequence. And it is measuring how far out in the sequence you need to go to have a small error. And it's a big number because it might be a long time before you're close enough to your proposed limit. As I said when I was reading the definition out loud, these are absolute value signs, and what we have is the difference between a term value and the limit. We're throwing absolute value signs around it only because we've seen that you can converge to a limit in a variety of behaviors. Sometimes the terms in the sequence are bigger than the limit, sometimes they're smaller than the limit. If you were looking at a sequence that converges to its limit from above, a sub n minus L would be a positive number. There'd be no need for these absolute value signs. But if you are a sequence that's approaching the limit from below, where the a sub n is a little smaller than the L, you do this subtraction and get a negative number, that just means that you're approaching from below, getting a negative number there, not just that you're close to the limit. So we're going to throw absolute value signs around the difference between the term value and the limit, because we don't know if an arbitrary sequence is approaching its limit from above, from below, or from all different directions if it's oscillating like the example we've shown here. So we're looking here at the difference between the term value and the limit and throwing absolute value signs around it because we don't care if it's coming from above or below. So really what this definition is saying is a sequence converges to a specific number L, which is its limit, if whenever we set some sort of small error, we can always find some particular index with the property that whenever we get past that index, I can guarantee that the error is small, that the difference between the term value and the limit value is a very small number. Last but not least, I want to show something cool that's going on in this picture here. Just as we did in those previous pictures, I've got the limit, which is the ideal perfection, going across right here. And our sequence are all these little dots, black dots, red dots, blue dots, orange dots. They all mean something different we'll talk about in a second. And they're all over the place. They're bouncing like our C of n sequence in a previous video. That error epsilon is giving us these ranges. There's a threshold from below, just a little bit less than the limit, the error amount less than the limit, this range above, just a little bit more than a limit. When we're looking for this capital N, we're looking for how long do I have to go on this axis until I can guarantee that all of my sequence values are bouncing in between these two ranges. The colors that we're seeing here on the slide is indicating that this blue value, its index, capital N, big N, is that index value for once we're past here, I can guarantee that everything falls within this range. One last very important thing, notice that some of these values earlier on were within the right range. But because there was a time after this N value where we jumped out of the range, I haven't gone far enough yet. The big N that I'm looking for will be an N such that we enter at this point and then always after there we stay within the bounds.